So this is one of those puzzles where it's cool that it exists, but probably wasn't designed with a solution path in mind. But there actually is a pretty elegant, logical course you can take to get to the solution of this puzzle. It's an anti-XV with a single little killer given as a clue. The start is pretty straightforward. Just looking at minimums along this diagonal. The minimum possible value I can put is already a 7. So we're 1 degree of freedom off that. This can be 1 or a 2. And in these boxes, these can be 1, 2, or 3, but must include a 1. The fact that I have a 1 in one of these two cells means neither of these two cells can be a 1. They also can't be a 4, because 4 would require a V with whichever one it touches. So 4 is going over here. These two cells also can't be 2 or 3, because it would make both of the cells touching them a 1. So these are from 5 and 6. These are from 2, 3, and 4. And we can do exactly the same thing in this box. And this is probably the sticking point, where, well, okay, what do you do now? And you can actually do something rather interesting with these two cells. What would happen if I make this cell a 4? Well, that's forcing 4 in this box up to here, but it's also the 6 in this box. It now has to avoid touching a 4, and there's nowhere I can place it. So this can't be a 4. Same thing happens if I try and put a 4 here. In order to avoid having a V between these two cells, the 1 gets shunted down here, the 4 gets shunted down here by Sudoku, and now I need a V between these two cells. So actually neither of these two cells can be a 4 without breaking the box. So 4, and because we have the 4s up here, in this box, must go in one of these two cells. And having 4 in the middle of this box like this is rather interesting for the 1 and the 6, neither of which can go next to it. If I try and put the 4 here, then 1 and 6 have to go up top in order to dodge it. And if I try and put the 4 here, then 1 and 6 have to go down below in order to dodge it. So we get this interesting sort of pattern where either this is the disposition of 1, 4, 6, or this is the disposition of 1, 4, 6. And we can extend that over into this box. If this is the 4, this is the 4, and this is the 1, 6, because 1, 6 up here force them down here, and they can't be next to the 4. And vice versa, if this is the 4, then 1 and 6 get shunted up here. So we've got this interesting sort of coloring pattern on 1, 4, 6s and 2, 3, 5s. And we can do exactly the same for these two boxes. The logic is identical. If I try and put a 4 in either of these, 4 here would go 6, 4, which is no good. And 4 here would go 1, 4, which is no good. So we get 4s in the center. We can color two patterns. Either the 4s go like this, and the 1, 6 is like that. Or the 4s go like this, and the 1, 6 is like that. And now that we've got these two coloring patterns, we can ask which coloring on blue-green is compatible with a coloring on purple-green. And there are a lot of orange cells touching purple, and a lot of blue cells touching green. So it's going to be a problem if I try and make blue the same as green. Because if blue-green contain the 4, 1, 6, then these two dominoes are broken. They'll have 4s here and 1s and 6s here. And if I try and make orange-purple the 4, 1, 6, then these dominoes are broken. They have a 4 here touching 6s here. So actually we know that blue and green are incompatible for 1, 4, 6, and orange-purple are incompatible for 1, 4, 6, and therefore blue must be the same as purple. And orange must be the same as green. And now this coloring on the upper portion of the grid is going to give us some more interesting logic. For one, we know the 1s in this group, they're either going in orange, so here and here, or in blue, so here and here. But either way, there's going to be a 1 in one and exactly one of these two cells. So these guys which are touching them, they can't be a 1, because they would be next to a 1. They can't be a 2 or a 3, because if I put a 2 or a 3 in these cells, it eliminates 2 and 3 from these two cells, and they would have to both be 1. We've just established why that won't work. So these can't be 1, 2, or 3. They can't be 4. So they have to be 5 or 6. And now what this allows us to do is it allows us to do a little bit of coloring on cells like this. This has to be a 2, 3, or a 4. So in this box, it now can't go here. It has to go here, which places it here in this box and here in this box. These cells are all the same. And that means that this 1, 2, 3 in this box is going here and therefore here. So these 1s, 2s, 3s on the diagonal are the same. And we get exactly the same thing happening with this cell. It has to go here in this box, and therefore in one of these two, but it can't be a 5 or a 6, so it has to go here. And here in this box, these are all the same. So this 1, 2, 3, which now in this box can't be green and can't be 5 or 6, has to go here. So actually, these two cells are the same, and these two cells are the same. And what that means is that this section of the 8 diagonal collectively add up to an even number, because they're twice the box sum. And that means that this cell has to be a 2. That makes the rest of this diagonal add up to 6, so each box has to be 1 and 2. More importantly, this 2 eliminates 2 from both of these two cells, and it eliminates 3 from here. So we actually know this green cell is our 4, this red cell is our 3, and now the puzzle is going to start quickly collapsing. These 4s mean that this blue is going to be our 1, 5, 6. And the orange is going to be our 2, 3, 5. And just like that, we're through the puzzle. And all it took was a little bit of coloring. Hope you enjoyed. I'll see you later.